Welcome everyone. We're Team 1 and this is our Lab 6 presentation. So today, just as a bit of an overview, we will be covering our sensor board design, how we sent that to manufacturing and ordered it, all the components that we would need, how we tested it, and what results we got from testing in the lab, our team contributions, and then a small video demonstrating our closed loop control. So looking at our sensor board design, the initial design schematic was provided to us from our instructors. This was given to us at the beginning of the semester, and it represents our voltage sensor and our current sensor and has pin connections for each of them. Our voltage sensor consists of a voltage divider, an amplifier, and an RC filter. Our current sensor consists of an IC chip, a buffer, and also an RC filter. For our voltage sensor design, we were told that we'd be given an input in the range of 0 to 100 volts. This will be represented by signal A in our block diagram. From there, we hit our initial voltage divider with a gain of 1/10. This produces signal B from our block diagram, which is in the range of 0 to 10 volts. From there, our amplifier brings that down by another 1/5 down to 0 to 2 volts. Lastly, signal D comes from our RC filter. The voltage divider at the end of our current sensor and voltage sensor will not be used. For our current sensor design, we will use the same voltage divider that our voltage sensor had. And again, the voltage divider at the end of our current sensor will not be used. Our IC chip generates 0.2 volts for every 1 amp of current that passes through V positive to V positive 2. This is known as our sensitivity and can be found on the data sheet for that IC chip. We are told that the input to our current sensor will be in the range of 0 to 10 amps. This will be signal A in our block diagram. Our buffer has a gain of 1 volt per volt. And then, as previously mentioned, our current sensor will utilize the same RC filter as the voltage sensor. Looking ahead, Christian will cover our PCB design.
Okay. The PC board was initially built in Cadence PCB editor by importing the initial design given to us at the beginning of the semester. Footprints were also provided to our team by the instructors. At first, a netlist was created so that a PCB editor could know where to reference each component that we were placing in the design. And the PCB board consists of 4 layers. Top and bottom layer are for signals only. Second layer is for plus or minus 5 volts, our power, and the third layer is comprised of a copper core that will act as a ground plane. It's important to separate these signals as you definitely want a common ground between all components, and you don't want power and signal on the same layer. That can lead to problems. Lots of noise and output as well. It's important to notice that the copper cores for the current sensor do not overlap the ground plane, as this would create a capacitor. Also, the IC chip is separated from the rest of the circuit due to the high amount of power flowing through. As you can see in the image, top and bottom layer, those are our green and yellow signals. Second layer blue, that's going to be power, and third layer is ground. Okay. Our PCB board, originally we looked at 4pcb.com to try to order our board. That's where we did our artwork file and Gerber file checks. That was extremely expensive to order from, and thanks to the instructors, we were able to find a website called jlpcb.com. This is where we ordered it. At first, our board was larger than 4x4 inches. That was part of our design. We wanted to be able to solder really simply, as there was no size constriction on the board originally. But we noticed when we went through the checkout, there was a $35 engineering fee. And thanks to my team, we were able to discover that was due to the size of the board. We went back in, changed a few things on our design, and were able to remove that $35 fee from the cart. The board size now is 4 by 3.52 inches. The total for the entire order of 10 boards came out to be $26, including shipping. The reason we ordered so many boards is, one, so everybody on the team could have one at the end, kind of to look back and remember what we've done in here. And second, the boards were super cheap, and plus we wanted to have, in case we messed 1 or 2 up, which we ended up doing once. It's always good to have extras. So all of the components were ordered from digikey.com. The components selected were determined based on the signal flow charts mentioned earlier. All of our resistors and all of our resistors are in the range of 10 kilo ohms to 100 kilo ohms. I think we have one or two 200 kilo ohms in there. We don't want a lot of current flowing through any part of our board unless it's intended over near the current sensor. So all we want is to pass voltage through. All of the bypassing capacitors and RC filter capacitors were chosen to be 0.1 microfarads. This design choice was made based on the recommendation from the instructors. The RC filter at the end was designed to have 3.2 kilo ohms and achieve a cutoff frequency of 500 hertz. It's also important to notice that a lot of our resistor values that we ordered were simple values, such as 10 kilo ohms, 100 kilo ohms, stuff like that. It's a lot cheaper to order rather than a 4,122 ohm resistor or something like really specific. Next, Ivy will discuss the voltage and current sensors.
The three figures below were captured from the oscilloscope in the open lab. They display the input voltage and output voltage of our voltage sensor. The result matched with our design with minimal error, which was due to the tolerance of the resistors. The expression we use to calculate the output voltage is 1/50 times Vin. The first figure shows that the amplitude of the output voltage, the input voltage was 5.2. The next one is 10.2, and then last one is 15.2. The next is current sensor testing. The PCB current sensor was tested by placing the sensor in series with the inductor. The current sensor was functioning as intended by generating a sinusoidal voltage within the range of 0 to 3 volts. In the figure below, the peak-to-peak voltage of that is 490 millivolts. At the end, the voltage and current sensor met all the requirements. Next, Stephen will talk about the configuration building in Simulink.
Hello. All right, so initially we were given the Simulink design from the instructors. And as you can see, we have a hardware interrupt, triggered subsystem, a rate transition, and EPWM to help produce the signals. The interrupt is known to act as a delay, which helps changing variables, by output variables within the system to act accordingly. The rate transition also provides the sample time associated with the output. And we know that the pulse width modulation provides our switching frequency. All right, so this is actually inside the triggered subsystem. As you can see, there's an ADC block pretty much connected to an offset, a couple gain blocks, a moving average that enter the PAI controller. We have a discrete sine wave subsystem to produce the actual sine wave. We have the duty cycle ratio, and then we have in the bottom right corner the modulation index for open loop control. So, like I was stating, those are all the components. The actual system allows for open loop and closed loop testing. As I stated before, the open loop is actually utilizing the bottom right portion where the product is connecting the sine wave to a modulation index. The modulation index is changed from 0 to 0.5, and et cetera, to actually produce and view the output. The closed loop connects the entire system, which is usually the ADC block. And to actually do this with the sensor board, we connect the I sensor from the J4 pin to the ADC, which is in the J3 pin 29, to actually get the closed loop control waveform. Within this test, we actually had to change our offset and our gain and our KP and KI values to achieve a pretty good signal. So next will be Forrest going over the lab results. Thank you.
In the lab, we set up an open control lab on the oscilloscope in the open lab. And during that, we found that the actual voltage was 20 volts peak to peak, or just 10 volts peak. And then an actual current was then captured through measuring the difference in voltage captured on the oscilloscope, which was found to 0.5 amps. Here we have the results of the closed loop control. The first one on the left is going to be the 1 volts peak to peak. And then, oh, sorry, I got confused. It's actually just a set to 0.5. And then on the next one on the right is going to be set to 1. And then on the closed loop control on the second slide, the loop is then at 1.5. And then the next one on the right is the transient response from 0.5 to 1.5. Here are our team roles listed out. And then next I'm going to play a demonstration from the lab of our closed loop control system.
That will be the end of our demonstration video. I just want to give a big thanks to all the instructors, Ali, Dr. Parkby, everyone who helped us out through the semester. We couldn't have done it without you. And I also want to give a big thanks to all my teammates for this video. We knocked it out this semester. We did great. I'm proud of all of them. So thank you.